Hello everyone, this is Yusong Deng and I'm a student from Franklin Marshall College. I'm recording this video as an introduction to the whole series of video we are going to make in the next few months talking about the deep learning architecture and from a mathematical approach. So before we start, let me introduce myself a little bit. My name is Yusong Deng, or you can call me Sebastian. That's what most of my friends and professors call me. And I'm currently a rising junior of Franklin Marshall College, majoring in mathematics and applied mathematics. So that's my basic information, and let's begin. So in today's video, we are going to talk about three part of things. First of all, a general introduction about the goals of this series of video, the content we are going to use, we are going to talk about, and the second part is an introduction problem to the whole things we are going to talk about from a mathematical perspective, using many examples that you have seen many times in your learning experience. So those are really simple questions, but we look at from a neural network perspective, a deep learning perspective, that they are really interesting. And the third part of this video, summary and looking forward. So basically, what we are going to do in the future, and we will revisit the question we put forward in that section later in the series of videos. So that's what we are going to do. Let's begin. First of all, introduction. So the goals of the video series. As you know, that I'm a math major from Franklin Marshall College student. So I'm currently taking or selecting a class, a course we call Math 391 or 491, it depends. But directly reading, basically a professor will take me to do some reading on some interesting content that we not typically offered in the college. So in the next few months, Professor Brody will teach me a little bit about deep learning architecture using the book we are going to talk about. So that is a really amazing opportunity. I think it is also good to record a series of videos to lapse something behind me and to testify how good I understand the content of the book at the same time. Because if I do not try to talk them out, I may not be able to understand that I have something not perfectly understand through the reading process, and that is not definitely what we want. So first of the goal is that this is for courses. This is for course, and so the second thing is what I think the most important for now, to introduce the mathematical insight of deep learning process, to tell you how to analyze a process, or analyze a deep learning process from a mathematical perspective, and to illustrate that this is not like a black box, like something magic that you cannot explain with some most basic knowledge. So that is the second goal of this series, which is what we are trying to do, to tell you a little bit about, okay, how is it like from a mathematical perspective instead of a computer science perspective. I know many of you touch deep learning by taking computer science class, but I think the majority things talked in that class is how you use TensorFlow, how you use maybe PyTorch, or how you construct a neural network, instead of tell people, okay, this is what happened in that process. All right, so that's two goals of the series. And here's my contact information. The reason why I leave it here is because well, I'm making this series of video. It is also the first time I read the book and learn deeply about what happened, what talked in the book. So it is inevitable for a first-time learner to make some kind of mistakes and to omit some details. So if you, while you are watching this video, if you found that there are something not proper or there are something wrong, please feel free to reach out to me and contact me about your concerns, about what do you think, so that I can in the future make some makeup video to correct my mistakes. Of course, everyone will make mistakes, and as a rising junior, I think I will make more mistakes than normal people. So please do me a favor and feel free to reach out to me if you think something is not okay or not right. Okay. So this is the book we are going to use, The Deep Learning Architecture, a Mathematical Approach by Dr. Collin. So this book was occasionally found by me when I wandering through our F&M library collection, because we have a Springer subscription. So we have almost all the books published by Springer. And so this book, The Deep Learning Architecture, a mathematical approach, is really amazing. And so at that moment, I was taking a class with Professor Brody. He read the book as well, and he's so nice to offer me this opportunity to work with him on doing some deep reading into it, digging some things, some fantastic mathematics out from the book. So if you are also a FM student, or your institution got the Springer subscription, Springer collections. So I think it is not easy, not hard for you, not hard for you to retrieve it from your library system. So that's a book. And so there's one more thing actually I would like to talk before we really head into the book, that is the audience. As a rising junior of liberal art college, I don't think you should expect me to know everything in the mathematics really well. Actually, it is really hard. Merely there are people understanding each field of mathematics really well from my perspective. And so it's even harder for me to tell you precisely about how things work in each field. That's why in some part of the video, you may see that I scramble from point to point, because I am not so sure about what I'm talking about at that moment. But for the audience, I have to say, on the other hand, that the audience should have the most basic knowledge in almost every field of mathematics, because this field, this book we are going to use is talk about is a pre-graduate book, or say graduate first year textbook. So there are something not hard but fancy about mathematics, such as the functional analysis and many things in advanced linear algebra. So that's something you should definitely know before heading into the book. Otherwise, it will be a little bit hard to understand what really happened through that process. But trust me, it's never hard. It's just a little bit fancy. And if I do not specify about the image I use in the following in the series of videos, such as this one, if I do not specify where it comes from, it is coming from this book, and I will try to notify you when we reach them. Okay, so let's head into chapter 1, some introduction problems. I picked this 4 problems I think are interesting out of the total of 8 or 9 problems talked in the book. So if you are interested in that, you can definitely head into it, head into the book and read more problems to have an idea of the introductory problem. So first of all, water in a tank. Many of us from primary school must be suffered from this kind of question. Okay, there's a water tank, someone is pouring water, or pipe is pouring water into the into the tank or swimming pool, and at the same time, someone forgot to close the knob of draining the swimming pool or water tank, and then so the swimming pool is also draining at the same time, and people will ask you, okay, after how long time will this water pool be out of water or be full? And at that moment, I don't know you, but me have this kind of question: who the hell will do this, right? We want to save water resource. We do not want to waste it. So with many water here, do not drain and pouring it at the same time. But later on, as we go on to more mathematical things, you will realize, okay, it is an interesting differential equation problem, or say you can even consider it from a dynamic process, right? There is, and also if you are a rocket engineer, you know that how we pouring oxygen and avoiding the oxygen to explode because of some physical change of its status is also pouring and draining the oxygen at the same time with different rate to keep the pressure in the tank at a proper level. So here we reach to computer science, we reach to neural network. We will say, okay, water in a tank is still an interesting question to discuss from a perspective of a neural network. So let's see, here is one of the basic things we are going to use. This is a water pipe, and here's a knob that can adjust the rate of water being poured into the water tank. So here we have, excuse me, this is a pipe and a knob K, and the water pipe will supply the water at a given pressure P. So the outgoing water rate R can be adjusted by a non-negative control W added onto the knob K. So we have this one, P equals to R over W, or R equals to PW. It's okay, whatever you said, but this is the setting here we have. All right, so let's look at this. For now, you have a tank, and here are some volume of water, and you have several pipes. You have N pipes actually, and so a certain number of pipes are pouring water into the tank. Here are N we have, and at the same time, the tank, sorry, it's not time, the tank is drained at rate R. So here they are pouring water into it and they are draining it. So the question is, given the water pressure P1, P2, P3 to Pn, how can we adjust the knob K1, K2, K3, such as after a fixed interval time T, so that is predetermined, and there are required volume V of water in the tank? Just several seconds for you to think about the question, right? This is our question. We want to adjust those knobs. These are only things we can adjust. We want to adjust the knobs so that after several times there are certain water in the tank. So first of all, most obviously case is that R greater than the sum of Ri, right? Because no water will accumulate because the drain speed is larger than all the input, right? And so in that sense, what will happen, right? V equal to 0 for arbitrary T, because whatever you pour into it, they are always going to be drained out by the drain tube or pipe, right? So here, we have a less boring case that R is smaller than 1, which means, okay, water will accumulate. Obviously, the case water will accumulate through times, and the rate of accumulation definitely depends on the difference between the rate of pouring and draining, or saying that mathematical formula is this one. This one is the rate of pouring, and this one is the rate of draining. So we want to know, okay, what is the difference between them? How much larger is the pouring than the training. So we have this one, the volume. The volume is to sum up the above two cases. The volume is either 0 if this one, or it will accumulate through time otherwise, which is really simple, right? So let's consider an activation function, such as activation function. Don't worry if you do not understand what is an activation function. We will talk about it later in the following sections. So don't worry, just now think it as a function. So this function phi x equals to 0 if x is smaller than 0, and equals to x times t if x is otherwise, or saying greater or equal to 0. So let wi be the control provided on each knob k, such as by what we discussed before. We know that ri equals to pi times wi. So now the function of volume can be written as v equals to phi t, this one, sum I to n pi wi minus r. So just a reminder, what we have before is this one, volume equals to this, and we just substitute r with pi wi and try to write the function into one function. Okay, so the problem now reduced to the solution of this equation. With wi and r is unknown, we don't know what rate r is, and we don't know the relationship between r and w. Means we don't know the mathematical. We know the how to say that, the idea of their relationship. We know, of course, they got a relationship, but we don't know what precisely is the relationship. So in practice, we can choose to find an approximation of the solution by minimizing the following function. The first function is this one. So this is the things we want to minimize, and this is actually a distance between the target volume and what volume you will have. What volume you will have in your idea, right? So this is one kind of method that you can calculate the distance between those two things, the things in your idea and what's your target things, to minimize it, which means if the distance between them are really, really small, you can say, okay, we got a good approximation. Sometimes the approximation may be too good, but it is still a good approximation. Or saying that, okay, this is another things we can minimize, and this is really, really straightforward. That is just the distance between them, but just there's something, because this one is not smooth. If you look into the function, you will find out, okay, this function is not smooth. So we do not want to use it here because of some reason that we will talk about further in the cost of functions section. So we will use this one here. We will use this one here, and this one is actually one of the most widely used cost of function we will see in the future. So in practice, we want to learn from data. To achieve this, we are providing untraining data with the pressures and corresponding volume at time t. So we will have pk and vk. K is sorry, this should be small k. K is greater or equal to 1 between 1 and n, and the pk is actually a vector, or you can think it as a matrix, is all okay, and the pk in pk transfer, that one. Sorry, my language, equals to pk, p1k, p2k to pnk. So then we should be able to forecast the volume of v after giving untraining data of a vector of the pressure vector p. So this contains minimizing the following cost function. So it is still simple. I just write them as vector form, which is pk, the transform, and times w minus r minus vk to the power of this one, and w t equals to w1, w2, w to the wn, which is the adjust you add on to each knobs. So that is, and that is the solution of what we have. How to minimize that is another thing that you are expected to learn in the computational mathematics, or more things, minimizing things, optimizing things. So I won't go into details of that here, and let's head into our next question. So this question is actually the 8 roots problems. Is actually famous problems in combinatorics, right? Many of you, if you are learning about combinatorics or more generally discrete mathematics, I'm sure that you will see this question once or twice at least. And you have many informal ways to solve it. You have many idea to solve this problem from a discrete mathematics problem. And so, but today we are going to solve it using computational perspective. So here, as you can see, is the solutions of the 8 rook problems on a 4x4 chessboard. So basically, what is the 8 rooks problem? The what I present here is not 8 rook problem; it is a 4 rooks problem. So basically, you have 4 rooks. And the rooks are required to place in this way, that each column and each row can only contains 1 rook. Each column and each row can only contains 1 rook. Only 1 rook. Okay, is that clear? I think so, right? As you can see here, in a 4x4 chessboard, you have already many solutions. For example, you can just put them simply on the diagonal, and that is one solution, of course. So let Xij, how we going to, sorry about that, how we going to solve them from a neural network perspective or computational perspective? Let Xij be the state of Ij square, and so we define it to be in this way: Xij equals to 1 if there is a rook in Ij, and equals to 0 if there's no rook at that position. So basically you can see, okay, this place is 0 because no rook is there. This one is 1 because 1 rook is there. This is 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, right? So that is the thing, how we define it. And we can use the state representation we constructed to construct an objective function. So first of all, we begin from here. Because there's only 1 rook placed in the J column, which means there's only 1 row in the J column that has a rook. What does that mean? That means if you sum up all the row of the Jth column, it must equal to 1. So as you can see, we do not, we are talking about 8 rook problem, but a 4 rook problem is still enough to represent some ideas. So if I have a rook in the 3rd column, that means all the rows sum up in 3rd column must equal to 1, because here is 0, this is 1, this is 0, and this is 0. So it must sum up to be 1. Okay. So the second part, and let's continue that the fact of that property, of the property we just talked, holds for all columns. Okay, right? So column 1, column 2, column 3, until column 8 all follow this kind of relationship, which means if you want them to sum, if you want them to right. If you want them to, yeah, how to say that? I'm so sorry. If you want them to be placed in a proper way, that means each column must only have one, uh, one rooks, right? Each column must have one rooks, and so here we can construct to a function. We sum up all the column, and for each column we sum up all the rows and try to tell you, okay, if that is one or not. Why? Because you can see here, if there's more than one rook in that column, this will be one. And for example, there is a two rook in some column, we say column 3. The value here will be 2 minus 1 equals to the square, right? That is 1. If there's no rook in that column, that will be also 1 as well. Only when there's only one rook in that column, here will be 1, and this will be 1, and this part will reach a minimum, which is 0. So if you want to achieve that goal, that each column have only one rook, you want to definitely minimize the function in this way. And similarly, if you can achieving that each column have only one rook, in the same idea, you can definitely construct another thing to say, okay, I want each row only have one rook. So those are two things that we want to minimize. You want to minimize this one to achieve each column only have one rook, and you want to minimize this one to achieve each row only have one rook. So then the rook problem being reduced to this way. Even though the rook problem has many solutions, as you already seen, you can put it as diagonal, and you can diagonally shift it up or down. Those are all solutions. But each of them will corresponding to the global minimum of this objective function that you sum up f1 and f2, which means you ask it to achieve that that there are only one rook on one. There are only one rook on each column, and there are only one rook in each row. So that is our cost function. However, the combination here, we have more things to talk about why the global minimum should match the minimum of these two functions. But that is not our main goal here. We want to tell you something about computational things. So, but generally speaking, the minimum of this function can be obtained using a neural network, specifically neural network called Hopfield network. And I don't expect that I can talk about that much about the book, because that is almost the end of the book. But if you're interested in that, you can definitely Google it and see more about the Hopfield network. So for now, let's continue. But that is the idea of the 8 rook problems, and you saw how you solve it from a computational perspective. All right. Next thing, linear regression. Linear regression. So many of you, if you are my classmates, from time to time, we have been through linear algebra many times in college, and linear regression is always a famous thing taught in almost every field of mathematics. So, but we want to say here that the linear regression thing can be naturally interpreted as a simple neural network. So here are two parts we are going to talk. First of all is the real value function, and the second thing is multi-valued function. However, I think the book talked about those two parts, but I think the idea between them are really similar to each other. So here we will just focusing on the real value function. All right. Let's consider a continuous function f from k to the m-dimensional real space, and K is a subset of n-dimensional subspace. It is a compact set as well. So let's construct a linear function that approximates fx in the L2 sense using a neuron with linear activation. Okay, you see the L2 here. That's why I say you need to know a little bit about functional analysis or real analysis here, because that is what we will talk about in the real analysis, the functional analysis on real space. So, but don't worry for now. L2 space is nothing fancy. You can just think it as similar to what you have already studied in the past years about the mathematical plane. So, the input of the continuous, the input of this neural network would be the continuous variable x equals to, this is also a vector x1 x to the xn, and it is a subset. Lies in actually K, which is a subset of the n-dimensional real space, and the output is the linear function Lx. Lx equals to this one. It is just what we defined, and where Aj are the weights and B is the bias. Aj are the weights of each input vector, and B is the bias. So here is just an example. This one is a biased element, and you just add it to the neuron, and here's x1, x2 to the xn. So you have weight A1, A2, AN, and you time them together, sum them up. Here the output is the linear function you have. For the simplicity, we can assume that L0 equals to F0, which means the approximation is happened around the origin. And that implies to you that B equals to F0. And for functional shifting or modifying, you can always do a vertical shift that can always make F0 equals to 0, or saying B equals to 0. So you can shift upward and downward to acquire that one. And the linear function is Lx equals to the sum J equals to 1 and AJXJ, because B equals to 0. Excuse me. So let's consider this constant function that measure the distance. Actually, it is also a L2 distance between Lx and Fx, and that should be this one, 1/2 the integral K, right? You can just look at the equation. That is nothing fancy, but the L2 distance. So let's compute its gradient. Is nothing fancy. Its gradient is calculated in this way, and just some simplification, you can get this one, the sum from J to 1 and Aj rho Jk minus Mk, and K is between 1 and N. So rho Jk equals to this one, and Mk equals to this one. So that is what we will have in the final. You can try to simplify it yourself and see if you can get the same result. So let's write that in a matrix form, and here the nabla is just an operator, and the nabla C equals to rho A minus M, and the nabla C equals to this one. Actually, this is a column vector, but we write it in row here. So it equals to this one, the partial differential of AY, and to AN, and rho equals to rho reverse equals to rho JK, which tells you a lot about what that matrix is, right? It is invertible, it is right? There are many property of it, and M equals to M1 to Mn. Still, rho and M follows the equation we write in Luster page, and the optimal value can be obtained by solving that nabla A C equals to 0 still, and that will solve you something to this one, some k from k equals to 1 to n, g to jk, mk, and gjk equals to rho inverse. So how to solve that is not what we focus here, but that is definitely some hard thing in computational math, I think. And but generally saying, if you solve that, you will get something here. Actually, you can just solve it, and how to compute it is another part of computational math. So that's it. That's what we have to do with the real valued function, linear regression. And what we are saying here, okay, as long as you adjust the AJ into this way, you adjust the AJ into this way, you can find a good approximation of the linear function you want to approximate. All right, so here we have the cocktail factory. The cocktail factory, actually the book talks a lot about it, but I think it's all okay for us to skip it a little bit for now. So basically you can still see there are some water tank, you pour into water, and there's a knob that you can adjust it a little bit. But the key things is actually for a cocktail factory, you need something like wine, water, sugar, so that you can get some sweet water, and you combine them all together to get cocktail. So in that sense, you can see, okay, here are actually multi-layers of the process that the adjust from say that the adjust of W32 may not directly influence what you have in the cocktail tank, but definitely indirectly influenced it. So that is some basic idea of deep learning and the deep neural network, instead of what we have seen before, that maybe one neuron or two neurons can help you solve this thing. So the idea of the book is, okay, the for cocktail factory, if you want the output to be really satisfying, the precise adjustment on all these knobs are influencing each other, and there are relationships that you can adjust, how much you can adjust them from layer to layer, which if possible we will talk about in the later part. So okay, that's all the introduction problem, and I hope you enjoy them a little bit, and those can give you a little bit insights about the abstract neural network, that the process is not a black box, it's not hidden in the shadow, in the dark of mathematics, but instead the idea of this kind of calculation, summing and calculating distance or minimize the cost of function, is actually what we have been through from time to time. There's nothing really hard there, and I want to stress that it is not a black box. In the future, we are going to explain it with more and more mathematics. So I hope you enjoyed it. It might be a little bit boring, especially with the costing function that looks terrible. So let's have some summary and looking forward. So we would like to address several questions. As you already seen that we can approximate a linear function, we can approximate the water tank, we can approximate the factory, and in the book it even talks about how, like, electronic circuit or the neurons in your brain, how they work. So you can approximate that, but still we want to ask, okay, what classes of function can be presented by a deep neural network? What classes of function can be presented by a deep neural network? Actually, in the later part, we will try to prove that any continuous function or integrable function can be approximated by a deep neural network, which is such a broad class of function that is satisfying. That's also why we call neural network the universal function approximator. So that is the first question we want to ask in the future. And the second question is, how are the optimal parameters of a deep neural network estimated? Basically, say in the cocktail factory, how can we adjust each knob to make one cup of perfect cocktail, right? And the third question is, how can we measure the amount of information which is lost or compressed in a deep learning network? For many of you, I'm sure that you have already know that the MINST system, right? The MINST database about recognized handwriting number. So basically you have, I can't remember clearly, but a 728 pixel image and with some gravity scale number there. I think that is the information carried by it. And if you want to recognize the number written in that small graph, you have to tell the user that, okay, this is 1, this is 2, or this is 3. And that reduce actually a over 700 digit number if you just using the plain representation method to 1 digit to say, okay, this is 1, this is 2, this is 3. And that is the information compressed or say lost in a deep learning network. We want to analyze that in the future. However, we cannot do that much in a really short time. As I said, this book may cost you 1 year of learning actually with a professor. So hopefully by the end of this year, by the end of 2021, we can help you to answer the first 2 questions about what class of function can be represented by deep neural network, or what class of function can we approximate. And the second thing is how our optimal parameter are estimated through through a deep neural network. Hopefully by the end of this year, we are able to answer those 2 questions. And for the third, we will try if we can, but from my perspective, for the interest of time, I don't think we can answer that question really well by the end of this year. All right. So what's coming next? As you can see, here are many common things in the neural network or in the introduction problems we gave before. In the 4 problems we talked already. You can see, okay, they all have some similarity things, right? Even though they are different problems, they are in different forms. The cost of function are in different way. But what you can see is what they all have an input as x1, x2 to the xn, and each part of it got an activation function, maybe linear or non-linear or some kind of stepping function we talked in the book. So that is another thing we want to talk. And what we always have to minimize our cost of function. We always have to say, okay, we want to minimize something. We want to make something the smallest and find the global minimum, or maybe even just a local minimum to say, okay, this is what we have here. This is what we want to study. Of course, here are many, many common things. And those common things are what we want to study in the neural network from a mathematical perspective. Always we want to find the most common part of different neural networks so that we can do universal analysis on saying, okay, this is how all neural network works. And that is a really ambitious goal, but that is also true. So in the following series, I hope you enjoy this one. It is not that boring, but it might get boring from time to time as we making more videos, and we will talk through the book from chapter by chapter about the activation function, cost functions, and more things in neural network. So that is what I think we are going to do, and I will see you in the next video. Thank you so much. Thank you so much.